Hi, guys. Okay, so let's look at chapter 10 on chemical bonding. This is from the book Introductory Chemistry by Tro. And this book is on the Libre text, and we are looking at the exercise problems from this book, from every chapter. So chapter 10, 10.2.1, there's a exercise problem which talks about the Lewis electron dot structure. Draw the Lewis electron dot structure for these. So what are the rules for that? So for the Lewis electron dot structure, we write the valence electrons, okay? And valence electrons depend on the valence electrons, and that's the group number. So you have to identify the group numbers. If you are looking at like you don't know where is phosphorus or where is argon or how many electrons there are. So look at the group number, look at the valence electrons, and then just put the dot. So these valence electrons are going to give you the, so let me just put the other way around. So look at the group number first, where the element is placed, group number, and then based on that, you're going to place the dots as the valence electrons. So phosphorus in group 5A. So how many valence electrons there are? 5 valence electrons. So how are we going to show it? We show it like this. Phosphorus like this. Ideally, you should pair them 1, 2, 3, 4, and 5. The unpaired one goes on the top. Okay, so that's the thing that ideally you should be pairing them. Don't just randomly place them, because there's a concept of lone pairs. Okay, argon is present in group 8A. So there are 8 valence electrons. And so how do we place them? 1, 2, 3, 4, 5, 6, 7, 8. So look in the periodic table where the element is placed. Okay. Next is the illustrate the transfer of electrons. Now here we are looking at potassium and sulfur. Where is potassium? Potassium is in group 1A. So always, their placement in the periodic table. So group number, valence electrons, and then based on that, because here we are looking at the transfer of electrons, so therefore we'll have to look at the charges also. So potassium has 1 valence electron, and then when it gives away that 1 valence electrons, it forms a positive 1 charge. Sulfur, on the other hand, is in group 6A. It has got 6 valence electrons, and so the charge is going to be -2. So that means somewhere here, 2 electrons have to be given by, like, not just the potassium cannot give 2 electrons. So we will have to have 2 potassiums. So here's the thing. So ideally, let's do this. Here we have potassium, group 1A. So illustrate the transfer of electrons. So let's put this here. So here is 1 potassium, 1 dot. Here is sulfur. We have 1, 2, 3, 4, 5, 6. Sulfur wants to have 8 electrons in its last shell. So the 1 potassium can only give 1 electron. So here potassium gives away that -1 electron. And then that's not enough for sulfur. So another potassium, it has to take that 1 electron from another potassium. So here is this, it giving away 1 electron. So this way we will have the potassiums will have basically, now potassium gets an octet, but potassium loses that electron. So potassium has a +1 charge. The other potassium also has a +1 charge. Sulfur has a minus charge, but sulfur now has 1, 2, 3, 4, 5, 6, 7, 8. Okay, -2 charge, sorry. Sulfur will have -2 charge. So -1, -1. Okay, so this is what they mean. Next is write the Lewis structure for Cl2. Now Cl2, chlorine is in group 7A, 7 valence electrons. Okay, charge is -1, but it's giving away, right? But so let's draw this here, the Lewis structure, 7 valence electrons. And here is this one. And here's another one. 1, 2, 3, 4, 5, 6, and 7. Okay, so in this case, what's happening? We will see that this chlorine has 7 valence electrons, and it acquires, or it shares that, or it takes that 1 electron from the other chlorine. So that is how this chlorine gets 8 electrons, an octet. The other chlorine also will do the same thing. At one point of time, it will take 1 electron from the other chlorine also, and this way, this chlorine also gets 8 electrons. So temporarily, 2 electrons are shared between the 2 chlorines. Okay, so let me put this in a different color. So 2 electrons are shared. All right. So this sharing of 2 electron leads to a 1 single bond. And how do we show that? So in this region of overlap, 2 electrons are there in the region of overlap. So 2 electrons, they are, so that allows each of the chlorines to meet its octet. So that's how you're now going to write it like this. So chlorine, that's that 1 electron. This is another electron. So they share that, and the rest of them are going to be together like that. Okay, so this gives you the Cl2. All right. Next is write the Lewis structure for CO2 and SCl2. So here again, in this case, chlorine. Let's put it in a different color. No, sorry. So this is carbon and this is oxygen. Okay. So this is three atoms, right? Basically. So there is a rule. Carbon has electronegativity lower than oxygen. Electronegativity. All right. How do you know that? Now, ideally, once you know the trends in the periodic table, then we talked about that. And so this is the table where you show the ionization energy and the electronegativity match. This piece right here. The increasing ionization energy means increasing electronegativity. So the electronegativity increases as you move in the same period from left to right. Okay, so that's one piece. So if you compare carbon and oxygen, you will see oxygen is more electronegative. Now, another thing is this page has the values. Here, this is another page, okay, where we see the values of the electronegativity. Okay, here we see the values of electronegativity. So we see that on the right-hand side are more electronegative. On the left-hand side are less electronegative. So what do we see here? That on the right-hand side are, of course, the non-metals, but you see fluorine. Fluorine has 4.0, and 4.0 is the maximum. So all these numbers, these are on the Linus Pauling scale. So 4 is the maximum, but chlorine and oxygen are also very pretty close. So they are also very electronegative. But as you see, as you move from left to right, the electronegativity values are decreasing. So you see carbon is less electronegative than nitrogen, nitrogen less electronegative than oxygen, oxygen less electronegative than fluorine. Now going top down also, they decrease. So you see here fluorine is 4.0, chlorine 3.0, bromine 2.8. So here also the electronegativity is decreasing top down, going from top to bottom. And diagonally also, if you look at fluorine versus sulfur versus astatine, fluorine most electronegative, then sulfur, then astatine. So it's decreasing. So top down, moving top down in the same group decreasing, diagonally also decreasing, left to right is also decreasing. So maximum, the highest electronegativity is of fluorine. So anyways, so that's one thing. And then if you look at the comparison between sulfur, because that's our next question. So let's just finish this here. Sulfur is 2.5, chlorine is 3.0. Chlorine is more electronegative than sulfur. So similarly, carbon is 2.5, oxygen is 3.5. Oxygen is more electronegative than carbon. So having said that, knowing that, so you're going to refer, let me put this here, refer to the handout for electronegativity, no comparison or values, electronegativity, values, values and comparison. Sometimes you may not know or could get confused. So anyways, so now we have this oxygen. So that's why carbon is going to be in the center. Okay. Now you put carbon in the middle and you put one oxygen on one side and the other oxygen on the other side. Now, whenever you do these, there's something very important that you need to do is the total valence electrons. Total valence electrons. So carbon has 4 valence electrons and oxygens each oxygen is, one oxygen is bringing 6 valence electrons, other oxygen is also bringing 6 valence electrons. So a total is how much? So 6 plus 4, 10 plus 6, 16, right? 12, 13, 14, 15, 16 valence electrons total. So those are the ones we need. So the rule is that first you are going to connect the center atom with the outer atom. So this has been explained in the lecture. Now, I have read the way they have explained in the book. It's not very clear. So just follow the steps. I've really simplified them in the lecture notes. So first count. So the rule is, first I count the total valence electrons. Second, identify if there are 3 or more atoms, you're going to identify the center atom. Which one is going to go in the center? The one that has a lower electronic, but not always. There is also another rule. Not always. It's always that the ability to make bonds. So carbon can make 4 bonds and oxygen only makes 2 bonds. So therefore, carbon comes in the center. Carbon gets in the center spot because of these two, factors, lower electronegativity and the ability to make more bonds. So now you have put carbon in the middle and you put the oxygen on both the sides. After that, what you're doing, you are going to connect them with a single bond. Okay, so with single bond, you have used 1, 2, 3, 4. So you used 4. How many are left? 12. So 16 minus 4 used. So this is left is 12 electrons. So we are going to place them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now, if you check, you're going to, when you check, always check. When you check, what do you see? You see that the oxygen octet is met, but its need to make the 2 bonds is not satisfied. Similarly, carbon's need to make 4 bond is not satisfied and its octet is also not met. So therefore, in that case, the oxygen, so obviously carbon is not, the octet of the carbon is not satisfied. Octet, carbon doesn't have 8 electrons and it's not making 4 bonds. Okay, so what is going to happen here? In this case, rearrangement. So we see that this oxygen gives its lone pairs. This oxygen also has to give the lone pairs so that a carbon can make 4 bonds. So now we have this new structure where we have double bonded oxygen to carbon and double bonded oxygen to carbon. But the lone pairs, now they spread out even more, which is better. That's Vesper theory. Right? What is Vesper? I've covered this in the lecture also. So go ahead and, look at that for more details. But Vesper is where the bonded atoms are not liked by the lone pairs. In other words, the lone pairs push the bonded atoms as far away, and these lone pairs, they also spread out. So 90-degree angle versus 120-degree angle. Which one is more? 120. So therefore, this is a more like stable situation. So this is, they're more spread out, okay? And this is the structure. Now, if you count the total valence electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So all 16 have been accounted for. Okay, that's the Lewis structure for CO2. Okay, now same story with the SCl2. Now, because I need more space here, I am going to just move this a little down so we can have more space for, maybe not. Okay, I'm not. Okay, anyways, so I'm going to just, you will have to refer to the handout for electronegativity values. Okay, so here is this electronegativity values are in handout. All right, now we are looking at the sulfur. So sulfur is, again, electronegativity of sulfur is lower than the electronegativity of chlorine. Okay, in other words, chlorine has a higher electronegativity. So electronegativity of sulfur is lower than the electronegativity of chlorine. Besides that, sulfur can make 2, 4, and 6 bond. So this also is in the handout. So refer to that. And then chlorine can also make 1, 3, 5, and 7 bonds. But chlorine is being bonded to a lower electronegative atom. So therefore, chlorine is only going to make 1 bond. Chlorine makes only 1 bond because chlorine is bonded to bonding to a lower electronegative atom. So in that case, when chlorine is making 1 bond, sulfur is also going to make only 2 bonds. Okay, so let's see. So sulfur can defy the octet. So we are going to put sulfur in the middle because, total valence electrons. So sulfur has 6 valence electrons coming from sulfur, and then the 2 chlorines are bringing 14. Remember, 7 2s are 14. So this is a total of 20 electrons we are going to place. And sulfur, because it can make more bonds, but sulfur has lower electronegativity. So therefore, sulfur goes in the middle. So here is a sulfur, here's 1 chlorine, and here is another chlorine. Okay, now you are going to connect them. So connect with the single bonds. So what do you get here? Connect with the single bond. So you have taken 4 electrons. So minus 4 electrons, and you are left with 16 electrons. Okay, so these 16 electrons are where now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And any leftover are going to go on the top. 12, 13, 14, 15, and 16. Okay, so that is the Lewis-Strauss structure. You have to check you get all the electrons accounted for. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So all 20 electrons have been accounted for. Now, it's remember the Vasper theory, valence shell electron pair, the repulsion. That means the lone pairs, the lone pairs do not like the bonded atoms, so they push them at an angle. So there's going to be an angle in this molecule where the lone pairs are going to be on the top always. Okay, so keep this here. Let me make a note of it. These will be on the top. Place them on the top, not like anywhere. Okay, so that's the structure. Next is the sulfate ion. Now, very interesting here, sulfate ion. Sulfate has 1 sulfur and 4 oxygens. So each sulfur has 6 valence electrons and 1 sulfur, and each oxygen has 6 valence electrons. Okay, so total is how many? So 6 here and 6 4s are 24 valence electrons, 24 electrons total. And then we have plus 2 more, plus 2 charge. Those 2 electrons are the charges, the 2 charge, the minus 2 charge. So we will be adding that. Minus 2 charge also. So this becomes a total of 32 electrons. All right. So that's one piece. So these are the total valence electrons. Next thing is the sulfur and oxygen. Sulfur can make 2, 4, and 6 bonds. Okay. And oxygen can make only 2 bonds. So the guy that can make maximum number of bonds gets like a priority precedence. So this is one driving force. Next thing is, from the table I showed you, the electronegativity of sulfur is lower than the electronegativity of oxygen. All right. So because of that, now you're going to place the sulfur in the center. So you identify the central atom, not just based on the electronegativity, because, for example, some atoms, their electronegativity is higher, but they're still placed in the center, such as oxygen in water, right? So the defining one is the bonds. The one that can make the max, that has the capability to make the maximum number of bonds. Now I'm showing you sulfur 2, 4, 6 bonds. Where is that? So again, refer to the handout for the bonding in the non-metals. So refer to handout for, bonding for the non-metals, bonds in non-metals. So that will give you an idea, and then also you will have to look at the electronegativity and then the trends, electronegativity values, and then keep that flexible. Okay, so ability to make the bonds always gets the priority. because that's what you're doing, Lewis structures, making bonds. All right. Anyway, so now you have here sulfur. Okay, 4 oxygens, 1, 2. Let me make this here because I would need that space. So sulfur in the middle, 1, 2, 3, and 4. Okay, now what we're doing, we're going to connect it with a single bond. So 1, 2, 3, 4. So 4 means 8 electrons have been used. So now 32 minus 8. What is left? 24 electrons. So let's put those 24 electrons on the outer atoms, because all the atoms that follow the octet, right? You will place the electrons on the outer atom. So all the these electrons, once you make the single bonds, after that, the leftover electrons go to fill the octet of the outer atoms except hydrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 24. Okay, 24 electrons. Now we have 24 electrons. So everything has been used up. So when you check, what do you see? You check for the bonding. Is every atom making the bond? Is every atom making the bond? Or and then the second thing is the octet. If they follow the octet, remember, sulfur can defy the octet. So based on that, based on this table, you will see that sulfur can defy the octet. And that generally, you know, in the polyatomic ions, you know, they defy, in polyatomic ions, they defy the octet. So they are not, they can follow the octet, they can defy the octet. Okay. All right. So here's sulfur, but regardless, if you look at it here, the sulfur's octet is being met. Oxygen, the octet of sulfur is met and oxygen is met. So we are good with that. But, and sulfur is making 4 bonds. So sulfur can make 4 bonds. So 4 bonds for sulfur, which is okay because sulfur can make 2, 4, and 6 bonds. Remember, so, but oxygen needs to make 2 bonds, and that is not happening. So what is going to happen? Rearrangement. Okay, so in this rearrangement, we see that one of the lone pairs comes, like it's like a coordinate covalent bond. One of the lone pairs is lent by the oxygen. So it comes in between oxygen and sulfur. And so that satisfied the double bond need for the double bond. Similarly, this oxygen can also do. But this is going to only happen only you know, very, very specifically. So now I'm just going to keep one color. So here, this one makes double bond. This one is making double bond. So now these lone pairs also spread out, and these 2 guys will now wait for their turn to make a double bond. Why? Because maximum sulfur can do is accommodate these oxygen's lone pairs and make 6 bonds. So if you look at the sulfur, sulfur is making 6 bonds, right? So 1, 2, 3, 4, 5, 6, 7, 8. It's defying the octet. It's defying the octet, but it is making 6 bonds, which it's supposed to make. Look at that, 6 bonds. So sulfur is good with that. But oxygen, 2 of the oxygens are making double bond, very happy. Oxygens have the octet met, very happy. Sulfur is defying the octet, but it's making 6 bonds. Sulfur is good, but somebody has to hold a negative charge. Who? The ones that are not making the negative charge. So it's these guys. All right. So this comes here. Then comes now. They have to take turns. It's very fair. So what happens now? The other two are going to hold, keep the negative charge. And these 2 guys will get a chance to make a double bond. So the charge is inside, and because of the lack of space, I cannot draw too many arrows here, but 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So these guys are now making, these guys will hold the charges, and the other one is making the, is keeping the double bond. And now this thing moves further. So this goes back and forth, but other possibilities are also there where we see, where we see a diagonally. You know, sulfur, this one is making a double bond, this one's making a double bond, this one has a single bond, and this one has a single bond. And so these guys are now 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. These guys will hold a negative charge. And the last one is the other. So these possibilities, okay, these have been actually confirmed. So now we will have double bond here, double bond here. 1, 2, 3, 4, 1, 2, 3, 4. Oh, sorry. Double bond here, oxygen. Okay. All right. And then here oxygen, and then here oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then here we have a negative charge. And then here we have a negative charge. All right. And then this goes like continuously. This keeps happening, shunting. And this process is called, this whole thing is called resonance. And these are the resonating structures. This is resonance. And this, all of them are called resonating structures. All right. So this is the Lewis structure of sulfate ion. All right. So this is all you have to show all the structures on the exam. Next is the Lewis structure of XeF2. Now in chemistry, xenon, you've been told that xenon does not make the bonds. Xenon is a non-metal, but you can change the reaction conditions. And yes, again, if you refer to the table, refer to table on bonding in non-metals in handout. And there you will see that handout, and handout is HO. Okay, so here you're going to see one thing, that xenon can make 2, 4, and 6 bonds. Okay, and yeah, the electronegativity of, the electronegativity of xenon is, the electronegativity of xenon is lower than the electronegativity of fluorine. All right. Next is the xenon is lower than the electronegativity of fluorine. Let me put this here, lower. Electronegativity of xenon is lower than the electronegativity of fluorine. Okay. So xenon is going to be the central atom. So this is very important you identify this. All right. Next is the total valence electrons. The total valence electrons are total valence electrons. So for xenon, we have 8 valence electrons, and there are 2 fluorines. Each is bringing 7 valence electrons. So it's a total of 14 valence electrons. So 14 plus 8 is 14 plus 8, 22. So that adds up, and this becomes a total of, so you add these two, and this becomes a total of 22 valence electrons. Okay, now add the 2. So here we are going to now place these 22 valence electrons. So how? So you put xenon here in the middle, and you put fluorine on one side. Let me just put this here, more space. Xenon, and you put fluorine on one side and the other fluorine on the other side. Now what you're going to do, you're going to connect them first with a single bond. When you connect them with a single bond, how many did you use? You used 2, right? 4. And then so 22 minus 4 electrons, and that gives you 18 electrons. So these 18 electrons are used to put the octet on the outer atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 have been used up, but you're still left. You have to finish till 18. So 12 gone, 13, 14, 15, 16, 17, and 18. So there are 3 lone pairs, which is fine. 3 lone pairs. So this is why, it's very important that you draw them, in the right. So VSEPR, valence shell electron pair repulsion theory, puts the lone pairs, the 3 lone pairs on the top. So don't just put them anywhere, on top. And the 3 lone pairs are on the top, and we see that the bonded atoms are pushed down at an angle. So this is an angle, some angle. So it's a bent structure with some, so it would be of the type, when we talk about the shapes, we are going to look at the shapes from the table. But right now, let's look at the shape of this one. Let's look at the shapes. Okay, because even though it's not asked, but let's look at the shape. So here is the shape. For the shape, you are going to refer to the table shape, and you're going to look at the ion type or the atom type. So where is that table? So look in the handout. Okay, look in this handout, and you're going to see this table. Okay, this is easier. It's a very easy table. Now here, what are we looking at? Molecule and ion type. Look at this, molecule and ion type. In molecule and ion type, what is the meaning? A, X, and E. So A stands for the central atom. So central atom, and so here you're not just going to look for the bonding. Refer to the table on bonding in nonmetals and shapes. For the shapes also, you will have to refer to the table. So from there we see the ion type or the atom type or molecule type is molecule type. Okay, which one? So A, X, E. A is the central atom, which is A stands for the central atom. So in this case, it's a xenon. And then there are AX. X stands for the outer atoms, and these outer atoms are 2 fluorines. So 2 fluorines becomes AX2. Okay, and then there are the E. What does E stands for? E stands for the lone pairs on the central atom. Lone pair on central atom, always on central atom. So which one is that? Lone pair on the central atom is Xe. Okay, Xe. So there are 3 lone pairs. So there are 3 lone pair on the central atom. So this becomes E3. So what type it is? A. So I'm going to remove this. Not needed. And I'm going to remove this also. So you get that. Okay, so now we have what type it is. It is AX2E3. Now you look at the table, AX2E3. AX2E3. AX2E3, this one. AX2E3. 5 electron groups, right? There are 2 bonded atoms. This one is the bonded atoms. By the electron groups, we mean 2 bonded atoms and 3 lone pairs. So these are 5 electron groups. So even if you don't get the electron groups, just look at the number of bonded electron groups. Bonded electron groups mean bonded atoms. So how many? AX2E3 is 2. Then comes the third one, which is the number of non-bonding. Non-bonding electrons are the lone pairs. That's what they mean. AX2E3 is the number 3. So there are 3 lone pairs. There are 2 bonded atoms. So the shape is what? Trigonal pyramidal, and that is the triangle. So if the question is asking you what is the electron group geometry, it is trigonal bipyramidal. And if they're asking you what is the molecular geometry, the molecular geometry is linear. So don't worry about it, why it looks linear, because when you drew the molecular model, so it looks like that. So here the molecular geometry is molecular geometry, that's the shape, is coming out to be linear. L-I-N-E-A-R, linear. Okay, and then the electron group geometry is that. So this is the shape of this XEF2 and then the loose dot structure. Now let's look at the shapes of more complex molecules. Now here we have one carbon, one CH2Cl2. So here we have same thing. So based on all that, now you get the process. So carbon is going to make 4 bonds. So carbon is in the middle. Carbon, electronegativity of carbon is less than the electronegativity of chlorine. And hydrogen electronegativity is obviously is lesser. So we are just going to leave it, that carbon, because carbon can make 4 bonds. And even though chlorine can make 1, 3, 5, and 7 bonds, but chlorine is not going to, carbon is going to be in the middle. Carbon gets the center because it has a lower electronegativity. Okay, because of that. Now we're going to put carbon in the middle, and on one side you're going to put hydrogen, and you can put another hydrogen here, and you're going to put the chlorine here, and you're going to put the chlorine here. So I'm just going to simply draw a very simple shape first, and then we're going to rearrange 1, 2, 3, 4. Okay, like that. So, oh, I forgot, total valence electrons. Total valence electrons. So carbon is bringing 1. So one carbon, 2 hydrogens, and 2 chlorines. So carbon is bringing 4 electrons, hydrogen is bringing 1 electron, chlorine is bringing 7 electrons. So what is the total here? So we will see 7 2s are 14. So 7 2s are 14. So here we have 14 plus 2. Sorry, 14 plus 2 plus 4, and that gives you 20. 16, yeah, 20 electrons. Okay, so out of those 20 electrons, 1, 2, 3, 4, 5, 6, 7, 8 have been used up. So how many left? 12. So where are you going to put 12? Not on hydrogen, because hydrogen doesn't follow the octet. Only the ones that follow the octet we will. So chlorine. So 1, 2, 3, 4, 5, 6. The other one is 1, 2, 3, 4, 5, 6. So all the 12 electrons have been used up. So check for the octet. Chlorine's octet met, carbon's octet met. Hydrogen doesn't follow the octet. Hydrogen wants to make 1 bond. Hydrogen is making 1 bond. Carbon wants to make 4 bonds. Carbon is making 4 bonds. And chlorine will make only 1 bond, because chlorine is attached with a less electronegative atom. Okay, so that's one piece. Now what do we see here is the molecular shape. So look at the ion or molecule type. So molecule type. So it is always with respect to the central atom. So what is happening on this around the central atom? What all species are there? So we see the central atom, A is the carbon, X. So there are 4 atoms, right? 4 atoms are bonded. So there are 4 atoms. So, and then E is the lone pair. Carbon does not have any lone pair. So basically this is AX4 type. Okay, so when it's AX4 type, where do you go? AX4 type is, if you look at it, AX45, and there's no lone pair on the central atom. So AX4 is, there is 4 bonded atoms, 0 lone pairs, tetrahedral electron group geometry. Tetrahedral is a molecular geometry, and the angles are 109.5. So here, the electron group geometry and molecular geometry. So here we see it is the tetrahedral molecular shape, right? Because it's so it's a tetrahedral molecular shape, but you have to draw it. So it is a 3-legged chair. So just like a chair, you place a chair, right? Like this, 3 at the bottom. So like that. So let's do this. We're going to place, let's put 1 chlorine on the top, carbon here. 1 chlorine is at the back, but the 2 hydrogens you can see. Okay, so the one that is on the back, you have to just put it as a wedge shape. Wait a minute. Let me just clean this up. Okay, so here, so back, this is the back. Okay, so 1 hydrogen here, 1 hydrogen here. So wedge shaped. So this is the right shape for the tetrahedral. You're going to draw it like that. Okay, now comes the ethylene, C2H4 geometry. Okay, so here we have ethylene, C2H4. What do we do here? C2H4. So hydrogen obviously will make only one bond. So this is C and C, one hydrogen here, another hydrogen this side, another hydrogen this side. So these guys will connect like this. This is how you will bond. Okay, but C2H4. So let's now, I forgot something. Total valence electrons. Okay, total valence electrons. So carbon, there are 2 carbons, each bringing 4 electrons. So we have 8 electrons coming from carbon. There are 4 hydrogens and each is bringing 1 electron. So we have 4 electrons here. So the total is 12 electrons. That's one piece. Carbon makes 4 bonds always. Okay, and hydrogen only makes 1 bond. That is why we placed carbons in the middle. Okay, and hydrogens around it. All right, when you place it like this, now you're going to check, is carbon making 4 bonds? No. So what are we going to do? We have to bring in a double bond between carbon and carbon. So right now, 1, 2, 3, 4. Let me make a different color. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Obviously, the double bond will put all the 12 electrons in place. Okay, so that's the structure. Got it? So 4, what are the 4 electrons? Double bond means two single bonds. 1 single bond here, 1 single bond here. So carbon is making 1, 2, 3, and 4. Okay, the other carbon is also making 1, 2, 3, and 4. So each carbon gets that. Each carbon has its octet also met. So 1, 2, 3, 4, 5, 6, 7, 8. Each carbon has an octet met. Hydrogen only wants to make 1 bond. Hydrogen is making 1 bond. Okay, so this is the arrangement. Now, in this case, this is a multi-shape. This is a multi-shape molecule. All right. So in a multi-shape molecule, what are you going to do? So in this case, let me bring this again. In this case, if you look at hydrogen, carbon, hydrogen, double bond, carbon, hydrogen, and hydrogen. So this side in the middle, these 2, this is a linear shape. This side is just flat linear. So this is linear. Now, this side is different, the other side. So this side is 1 electron cloud, another electron cloud, and then the double bonded carbon and carbon. Same thing, one side, another side. So it's a 3 electron clouds, basically. So with all around carbon, around each carbon, there are 3 electron groups, okay, or electron clouds. So what does that mean? So that means the AX3. Which ones are there? Carbon and hydrogen, then another carbon and hydrogen, and then carbon and carbon. So these are the 3 electron groups or 3 bonded atoms. So these are each a carbon is bonded to carbon is bonded to hydrogen, 1 hydrogen and another carbon. Okay, so it's the same carbon. This carbon is the same. It's not 3 carbons, but it's the same carbon. Okay, so in this case, we see that it is the AX3 type. So on one side, so AX3 type, look at this. AX3 type is 3, number of electron groups are 3. Number of bonded electron groups, bonded means bonding electron groups are the bonded atoms. Non-bonding is the lone pairs. So no lone pair. So it's the trigonal planar. So like flat 120 degrees. So this is the trigonal. So AX3 type, and that relates to the trigonal planar. So trigonal planar on from this side. Okay, these 3, this situation. Okay, so that's the shape. So this is how you will do. Next is the polarity of each one. Now for the polarity, look at the So these are the last two questions we have. You're going to go in the periodic on the table again. And if you look at the place where we have the electronegativity values, and this is on page 9. On page 9, you will see the values of the electronegativities are given. Now, when the difference in the electronegativity, look at this table 6.14, when the difference in the electronegativity is from 0 to 0.4, the molecule is nonpolar. And when it's from 0.4 to 1.8, it is polar. And when it's more than 1.8, it is ionic. Okay, so we are going to look at now the electronegativity values on page 9, table 6.14. Let's keep it like that. Okay, so here you are going to, let me write this down here. Refer to table 6.14, page 4 in handout. All right, now R, B, and F. Let's see if those values are given. R, B, and F. Rubidium, 0.8, fluorine, 4.0. So let's write down here. So for fluorine, 4.0, and rubidium is 0.8. So this becomes 3.2. Now, according to this table, 6.14, we see that when the difference in the electronegativity values, this is the electronegativity difference is more than 1.8, 3.3. So it's an ionic bond. So this is the difference in electronegativity. So refer to the table. So these are the electronegativity value and electronegativity value. So this refers to ionic. It's an ionic bond. Okay. Next is phosphorus and chlorine. So let's look at the electronegativity value of phosphorus. Phosphorus is 2.1. Chlorine is 3.0. So 2.1 and 3.0. So electronegativity of phosphorus, so was it? I forgot. So this one is, phosphorus is 2.1. Electronegativity value of chlorine is 3.0. So this becomes 0.9. So that is the difference in electronegativity. Okay. Just put this a little away. Otherwise, oh. Oh, 1 minute. Okay. All right. So just change the space here. So 0.9. So 0.9 is, now look at the difference in the electronegativity. When it's between 0.4 and 1.8, what is it? 0.9. So it is a polar covalent bond. Polar. So this is a polar covalent bond. Okay. Now, what is the meaning of polar covalent bond? So let's do it a little bit more here since we have space. So here is this phosphorus and here is the chlorine. And fine, this is the single bond in between the two. I think it's just one part of that. So just a part of it. So what happens is, because chlorine is more electronegative, a slight delta negative charge comes on chlorine and a slight delta positive charge comes on phosphorus. And you see the net polarity is towards the chlorine side, the push for the electron cloud. Now, if you are going to take a heat maps, so what do the heat maps look like? So here is the phosphorus and here is chlorine. And in the heat maps, we see that the electron clouds, this side, electrons spend more time towards this side. So this side is a hot side. And what about this side? This side is cold side. So this side, phosphorus side, comparatively is cold side. So this is how the polar bond looks like. Okay. Now we are going to look at whether the overall molecule. So this here we are looking at the net polarity. Net polarity is the sum total of polarity of all the bonds. Net polarity is sum total of polarity of individual bonds in the entire molecule. Okay, individual bonds in a molecule. So what do we do? In this case, we are going to take sulfur, 3 oxygens, 1, 2, and 3. All right. So here we will then 1, 2, 3, 4, 5, 6. All right. I forgot the, sorry, okay, we have to, so you cannot answer these questions unless you draw the Lewis structures. You have to draw the Lewis structures for these. So let's do this. Total valence electrons. So 1 sulfur and 3 oxygens. So each sulfur is bringing 6 electrons. Oxygens is bringing 6 electrons, each of them. So a total of 6 3s are 18 and 6 electrons. So this is a total of 24 electrons. Because sulfur electronegativity is lower than oxygen electronegativity. So sulfur gets the center spot, but at the same time, sulfur can make 2, 4, and 6 bonds. This is very important, guys. And oxygen makes only 2 bonds. So the bonding, because sulfur can make more bonds, sulfur is able to make more bonds. Therefore, sulfur is going to be in the middle. It's always a bonding takes the priority. Okay, so therefore sulfur becomes the central atom based on its ability to generate numerous bonds. All right, so now that's why we place sulfur in the middle, and you put the oxygens on the outside, connect them with the single bond. So how many did we use? We have used 1, 2, 3, 4, 5, 6. So 6 are gone. How many left? 18. So what are you going to do with the 18? 18 are now put on the outer atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. 18 electrons. All the electrons have been used. So, but when you check, you see that the sulfur, obviously, sulfur can defy the octet. So don't depend on sulfur, the octet. But oxygen's octet is met. Each of the oxygen's octet is met, right? Each of them have 8 electrons. But the octet, so let's write this down, octet of sulfur is not met, and the octet of oxygen, so sulfur is not met, but for the oxygen it's met. So this is a good thing. Next thing is the need for the bonds. So sulfur wants to make 2, because sulfur can make 2, 4, and 6 bonds, but sulfur is making 3 bonds. So that's not, stable. Oxygen wants to make 2 bonds. Okay, so none of these are being met. So what are we going to do? We are going to do a rearrangement. So when you do the rearrangement, what do? We are going to bring in the lone pairs. So this guy gives its lone pairs. This guy also gives its lone pairs, because sulfur can manage a maximum of 6 bonds. So now we have, after this rearrangement, this scenario. So we have sulfur, double bond oxygen. 1 second. Rearrangement. Oh, sorry. Oh, GEMENT. Okay, so here we are going to make oxygen, double bond sulfur, double bond oxygen, double bond oxygen. Now, what do you see? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's octet are met. 1, 2, 3, 4, 5, 6, 7, and 8. So the oxygen's octets are met, right? And the oxygens are also making 2 bonds. Sulfur can make a maximum of 6 bonds. So sulfur is making that. You see that? Sulfur is making 6 bonds. So it's doing the 6 bond, and then oxygen is, so this is a very happy state. So that is the structure for this. Okay, now comes whether it's polar or non-polar. So what are we going to do? So I'm going to do just one, because it's we have covered ammonia and other, in the lecture. So I'm going to just do one here. All right, here we are going to keep this in mind, that oxygen. So just first of all, look at the individual oxygen and sulfur. Sulfur, even if it's a double bond, it doesn't matter. So look at that. So look at the bond. So look at the electronegativity of oxygen, electronegativity of sulfur, and get the difference in electronegativity and see if this is a polar or non-polar bond. So sulfur is 2.5, oxygen is 3.5. So sulfur, oxygen 3.5, and sulfur is 2.5. So this whole thing becomes 1.0. All right. So when this difference in electronegativity is 1.0, what kind of bond is that? So here you see between 0.4 to 1.8 is a polar. So this is a polar covalent bond. So each of these are polar covalent bonds. Polar covalent bonds. Okay, so what does this mean? Let's do this again. So this means that sulfur, double bond, double bond, double bond, oxygens with these guys here. And so here we see that the pull is this side, it's this side, and it's this side. Okay, this side towards the oxygen, because oxygen is more electronegative. Oxygen gets a delta negative charge. This oxygen gets a delta negative charge. This one also gets an delta negative charge. And what about sulfur? Sulfur acquires a delta positive charge, but it's an equal pull on all the sides. So what happens? The effect cancels out. So equal pull on all 3 sides. And because of that, the effect cancels out. So because of that pull, the effect cancels out, then what happens? When it's canceling out, then what is the overall net polarity? Overall polarity becomes 0. The effect cancels out. So therefore, this becomes a non-polar molecule, even though it has very highly polar. So overall molecule is non-polar. All right. So keep that in mind. Next thing is, I'm just going to give you for ammonia, for molecules like NH3, right? NH3 looks like this. This is the structure, right? Water is like this. Anytime there is a lone pair, and I'm going to just look at this one also. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So if you have a structure like this, for these guys, for these type of molecules, okay, what happens is for these type of molecules, there is lone pair on the central atom. There is a lone pair on central atom. So they're always going to be polar. So they're not symmetrical. Central atom. So therefore, they're non-symmetrical. And because of that, there's going to be polarity. Okay, non-symmetrical makes them polar, all of them, all 3, and or similar examples. So that's one piece. So keep the lone pairs in mind. And remember, it's a VSEPR theory. So VSEPR theory, valence, shell, electron, pair, the repulsion. So these lone pairs, they are pushing the bonded atoms further away, right? So let's just put the dots also. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so these guys. Next thing is anytime, so that is also, that's going to make it polar. Besides that, all the polyatomic ions are polar. Okay, then all polyatomic ions. Because ions means that all polyatomic ions, they have charge. And charge itself means, you know, polarity. So charge induces polarity. So they are all going to be polar. So sulfate is polar, hydroxide, carbonate, ammonium, all of them polar. Okay, so that finishes this. And okay, so this finishes this part of this. This was a lot. Okay, all right. Thank you for watching. Bye-bye.